on behalf of Nuremberg Messe as organizer of PARTEC and PARTEC. Both events take place in co-location in Nuremberg, Germany in September 2023. PARTEC, as you can see the logo on that side, the other one, that side behind me, is the industry show for all experts in the powder and solids processing, and of course the place to be this autumn, to say September, sorry, I misspoke there. PARTEC is our renowned international congress on particle technology, sponsored by the VDI, Association of Process and Chemical Engineering. And the event also receives numerous support from other international associations and organizations, which we are very happy about. PARTEC sees itself as an international forum for research and development in particle technology, and it brings together scientists and engineers from all over the world and covers topics like particle formation, agglomeration and coating processes, and diverse industrial applications for particles. Well, our today's virtual talk revolves around particle technology for sustainable products and gives a glimpse of the upcoming PARTEC topics this year. And I would very much like to thank our three speakers of today who will take you through the session. Please give a warm virtual welcome to Professor Dr. Arno Kwade. He's Professor for Mechanical Process Engineering and Particle Technology and Head of the Institute of Particle Technology at Technical University Braunschweig. He is our current chair for PARTEC, just to name three of his various functions. Hello there, Professor Kwade. Professor Dr. Stefan Heinrich is Professor of Particle Technology at Hamburg University of Technology. He's also Director of the Institute of Solids Process Engineering and Particle Technology and the former chair of PARTEC 2019. Hello there. And last but not least, Professor Dr. Carsten Schilde. He is Associate Professor for Digitalization of Complex Systems at the Institute for Particle Technology of the Technical University Braunschweig and Head of Division. We are very much looking forward to your talks, dear gentlemen. And to you out there in the audience, thank you for being with us. I wish you joyful insights into your field of study, research, or profession. And then I will pass on. The stage is yours, Professor Kwade. Please begin with your talks. Thank you very much.
Yeah, thank you very much, Mrs. Lotter, for the nice introduction. And now we have time for our three presentations. And we will start with the presentation of Stefan Heinrich, who was the former chair, and he will give a little bit, let's say, view on the last PARTEC, but also what was developed in the last years, also regarding sustainable production, sustainable processing, and sustainable products. Afterwards, I will give you a more detailed insight into this direction of the new motto of the PARTEC 2023. And I think we will finalize then with Carsten Schilde, who will show you the possibilities digitalization has today, also regarding producing sustainable products, but also in general. And before maybe we start, before I forget that, today you have the last chance to hand in an abstract for the PARTEC. So today is the deadline. So please, if you haven't done that, do that today, and you will be on the PARTEC conference. And now I would like to hand over to Stefan Heinrich, who will show or give you some insights what happens in the last years, and especially on fluidization and sustainability. Stefan.
Thank you. Yeah, thank you very much, dear Arno. Yeah, for me, it's a great honor to give this presentation today, because I was the chairman of 2019 PARTEC, and so I have had a very nice experience on that PARTEC. Perhaps some first introduction about the previous PARTEC, though we have had a very large conference with many participants, and everybody is invited to continue this experience, to come to the PARTEC 2023. And as you can see, there was also a unique combination between the PARTEC and the PAUTEC. Here you can see some photos of our stand of the Institute at the PAUTEC, which is the world's largest trade fair for particles and bulk solid materials. And during that time, in 2019, we have had 550 participants from the PARTEC, which we expect to have also in this year's PARTEC. We hope so. And of course, there was also a very important event, the ceremony for the Friedrich Löffler Award goes to Carsten Schilde. So that was a very big event. Carsten, you are now an awardee of the Friedrich Löffler Prize. And what you can see here on the left-hand side is topics and the subjects of the last PARTECs. And what is still not included during that time is this hot topic aspect of sustainability and artificial intelligence. You can see something about modeling and simulation and some topics on renewable materials, but the sustainability was not the main part of this PARTEC in that sense. Yeah, of course, we have had the topic Particles for a Better Life, which is still valid. Okay, let's go a bit to the developments which has been done during the last PARTEC until now. We can see that fluidized bed spray granulation is still a very hot topic, so can be used for agglomeration or for coating and granulation, either to create very porous blackberry-like structures or core shell-like particles, onion-like structures. And this can be used for many applications, for the fertilizer, for the detergent industry, production of catalyst, or also of instant powders. In the meanwhile, we work on plant-based milk powders. Yeah, that is also a hot topic, which was not actual in 2019. So plant-based materials, the coating of enzymes in biotechnology. And what we have learned during that time is that we have a time schedule and a hierarchical landscape, so to say, of our different simulation approaches, which ranges from sub-micro versus micro, meso, macro scale. But nowadays we have also much better advanced measurement methods, and we have also the hot topic of scale up and digital twin, which came into this story. And therefore we should also focus in the talk of Professor Schilde on this artificial neural network and digital twin work, which has been done during that time. And of course, we can look into the particle structures by bonded particle modeling. We can also work and have extended the CFD-DM approach. I will later on talk about recurrence CFD for real-time simulations of the flow structures. And of course, the interaction with droplets. Question is what happens for the wet case. And finally, also the flow sheet simulation is of great importance in the meanwhile, though we can really simulate very complex connected chains of processes with solids, and also the instantaneous process, yeah, is of great importance. And of course, also the advanced methods for the measurement of particle micromechanics. As you can see here now in this chart, we can see, oh, here is some problem on my computer. You can see the collision between particles for the dry or wet case is nowadays measured, or that wasn't possible a few years ago. So we want to develop criteria at which point such particles might bind together and form agglomerates. And the computer is able to detect these collision events, to produce any kind of velocities, yeah, in translation and oblique direction, so we can calculate the rotation. And this is, of course, very important to simulate the probability of the uniformity of these coating layers and to evaluate model and the model and the parameters, the calibration, so to say, of the DM models. Yeah, so where we have done a lot of effort in this direction. Of course, also for advanced measurement methods, it is very important to say that lots of development has been done regarding temperature measurement, moisture measurement. One can also measure online in situ nowadays these properties for the particle as well as for the gaseous phase. The droplets can be measured, and also, of course, the question arises, what happens with a single particle, with a single grain? Are we able to measure the temperature directly in the process? And we are working on that topic with such modified impedance spectroscopy sensors in the meanwhile. What else can be said is that large amount of improvements has been done during the last years with respect to the MCFD simulations. In the meanwhile, that is a case study for the variation of the most important process parameters like temperature, air rate of fluidization, and the atomization gas and spray rate, and some more. And as you can see, that is this very important outcome. We can track now some quantities like solids concentration in the droplets on impact, the impact velocity of the solid itself, and the surface liquid evaporation time. That means that also the transport processes are in the meanwhile included: heat, mass transfer, evaporation. And what we get out of this kind of simulation is the stability criterion for different modes of operation: bottom spray, top spray. Yeah, these are hot topics which needs to be distinguished, meaning that we can distinguish between dry zone and the wet zone, and the residence time distributions can also be calculated. And another very hot topic is, of course, the question: how many nozzles do we need in order to get a uniform distribution, especially also for the continuous processing, and the scale up from the small machine to the large unit, and to predict also particle properties like roughness of the surface. And this strongly depends also on the amount, on the number of droplets and the uniformity in this reactor. In the meanwhile, we are able to calculate these out of this the MCFD simulations. But the next very big development has been done with respect to new measurement data, which we can detect, to develop also outlier detections. And here's an example there with respect to digital twin. We apply nowadays the machine learning tools. Here you can see temperature distribution and pressure drop versus time, and with such artificial neural network approaches, we are able to predict then the moisture content versus time. As you can see here, this is a measured blue line, and the orange line gives us the prediction from this neural network approach. And that is fascinating. You can see in that particular case, we have an increase of the moisture content, which seems not very clear from the very constant values here, but which is very obvious for such an overweighting of the system. And this can be predicted. And of course, also the sensitivity study of transient flow sheet simulations is the very next big step that we might prove such a steady state or unsteady behavior by means of flow sheet simulation tools. And for that, we have developed such a flow sheet simulation software system, which has been developed within our DFG priority program in Germany. and which stands for dynamic simulation of solids processes, meaning we have instantaneous processes, batch and semi-batch and so on. And we have also the distributed properties of the solids. Yeah, solids can have distributed properties like API concentration, very important for the pharmaceutical industry, moisture, particle size, and so on. And this came into this dynamic flowsheet simulation software tool Dissol, which is now able to simulate very complex flow streams. And we have decided to go with open access. So we have, so to say, an source code which can be changed. So we have an open source code, yeah. And for the maintenance, a new company has been founded as a spin-off from our institute, just to give you information that is now available for the community. It's open source based, yeah, which is very novel. One of the last slides will show you the big picture of the digital twin. So we can now also go the second way, that we work with such a recurrence surrogate assisted multiscale models, which describes the particle kinetics and also size distribution. But with such surrogate kernels and adaptive sampling, we can feed, so to say, the flow sheet with a surrogate approach, and we can compare this with the mechanistic flow sheet simulation tools and get information for optimal and model predictive control. Very important, control of the process. The hot topic is here the autonomous reactor concept, yeah, which is the underlying concept. So to summarize, we were able during the last years to improve the approaches for this kind of simulation of fluidized beds, getting also information about particle properties, especially also by using digital twins. That is a new hot topic during the last few years, based either on machine learning or on flow sheet simulations and recurrence CFD, which runs in real time, or faster than real time, meaning you need to do such CFD DM simulations, but by using such recurrence plots, you are able to be faster than the real time. Yeah? The original work has been done by Stefan Perker, Professor Perker in Linz. We have some current projects together, and with this database you can go on for such future time steps which can be extrapolated due to the recurrence flow patterns. That's really the beautiness of this work. What else is to say is last slide, that in the meanwhile, we are able, at least here in Hamburg, also to look into systems with a very high resolution with respect to time and local coordinates. We have the worldwide unique prototype machine of an MRI, which is in a vertical direction. And the new director of the newly developed Institute of Process Imaging is Alexander Penn, who came from ETH Zurich. And now we install such an MRI, which is 40 centimeter in diameter, so we can work with real larger lab or pilot plant scale fluidized beds, and which is up to 3 meters in height. So we can measure the fluidized beds with respect to temperature, phase distributions, also chemical reactions, and so on. And the next step is what is required, that we adapt this information into such a communication interface in the so-called knowledge module for the real-time data processing, which is based on flow sheet simulation and on control theories, to really have the online control of a large and small scaled fluidized bed system. So we can really adapt this information to such a system which can be used then also in the industry. Yeah, okay. Thank you very much for listening to me. That it was a very short overview about the actual the current development, and of course also the personal review to the last PARTEC. My comment is, please come to PARTEC 23. It's really a very important platform to meet each other, and I know that Professor Kwade is the best chairman on earth. He will do.
No, you are the best chairman.
You will do the best, and you are really an expert to combine all colleagues to a platform.
So Stefan, thank you very much for your really nice talk, especially showing all the great developments which we have seen in the last years, especially also regarding digitalization, but also new methods, measurement methods. And now I will go to my presentation. So hopefully everybody sees my presentation. Yes, also from my side, a warm welcome again. And as you already heard, for the new PARTEC 2023, we have the motto Particle Technology for Sustainable Products. Why I had the idea in this direction, because I think everybody knows about the climate change, the energy transition. And I think we have to do a lot of work in this direction. And I hopefully can show you in the next 10 to 15 minutes that particle technology can play a really important role in this transition and getting a more sustainable future. So after Stefan have reviewed the particle and also showed some current process trends, especially regarding fluidization, I want to come to the sustainable particle-based products. And first of all, some words why it is important. I think because we need new technologies, for example, batteries and fuel cells. And I think we are lucky because these rely a lot on particle technology and on functionalized particles and also processing of particles, which I will show you a little bit later. And but in general also, let's say for all the processes we have in granulation, comminution, classification, separation, and so on, we have to look on energy efficiency and also how we can save resources, like maybe also material. So that's also coming more and more into our focus. And another thing what is really getting more and more important, and also in a governmental group who is looking in this direction, is a circular economy. How we can install a circular economy in Germany, now for batteries as a very important topic, but also for other more classical products, because I think we in the moment, we rely a lot on primary materials from all over the world. And I think we have to come to a point which we rely on our own secondary materials, which we have in the country. And last but not least, digital tools. We just heard a lot about that from Stefan, but we will hear more about this new trend and also the new possibilities we have today. So there was really a large change in the last years to use these digital tools to get much better processes. So I thought about sustainable products and particle technology, and then I thought it should be, we can, let's say, separate it in three parts. So first of all, we can look on products which are based on particles and which increase the sustainability or which help us, especially for the energy transition or energy turnaround. And this is, for example, lithium-ion batteries or other battery types, which we will see in the future. So some examples are here, or one example is shown here. I will come to this in the next slide again, but also fuel cells with nanoparticulate carbon particles and also platinum particles or electrolyzers are products which have more and more interest, and there are really big research programs also from the government for these products. Then photocatalytic coatings, I think it's not a new story, but also this is getting more and more important to install that really. and that they also have a long life cycle. And maybe also hydrogen storage can be some point which is interesting for particle technology. For example, I know about a hydrogen storage paste, which is based on a particulate magnesium hydride. Coming back to the lithium-ion batteries, maybe most of you, but maybe not all, know that these batteries are composed of particles. So on the anode side, we have graphite particles or graphite and silicon particles today. And on the cathode side, these are lithium metal oxides or lithium metal phosphates. And in these particles, we store, let's say, the energy by transporting ions via the separator, via the electrolyte from the anode, or first from the cathode to the anode if we charge the battery, and then during discharging from the anode back to the cathode. And these particles, besides the active material particles, which are graphite and these metal particles or metal oxide particles, we have some carbon additives which are important for the electrical conductivity, some binder and so on. And as you see here, these electrodes are composed of particles. So these particles have to be processed, they have to be synthesized, they have to be recycled. And to give you an overview of what does it mean regarding mass, so the amount of particles. So if we all get these factories which are planned in Europe today, you see that we in 2025 already talk about 3 million tons of these materials, and in 2030 about 4 million tons. And so this is a really huge amount, and it's also in Germany, it's still a really big number. Okay, now coming to the next point, we have to design our products in a sustainable way. What does it mean from my point of view? So we should use materials which have a sustainable footprint. So for example, use secondary materials instead of primary materials, or materials which can be produced with a really minimum of energy and other resources. Then also we should maximize the material efficiency, and maybe also using submicron, or what we shouldn't name today, but nanoparticles can give us a way to do that, so that we have less material but have the same function, the same property at the end. For example, here showing it for drug particles. So if you decrease the size, you need much less drug particles to get the same function in your body. And also we should think really by designing a product about their reuse or the refurbishing, or especially also the recycling of this product. And if we do so, then we can really keep all the material in a closed material circle, and we come to a really efficient circular economy, hopefully in the future. And I think the particle technology will play a major role that we achieve this goal. And I know that the governmental the ministries are really pushing this theme for the future, and we will probably get a lot of new rules that we have to fulfill to come to this point. And I want to show you this as an example again for batteries. So in the moment we use primary materials coming from different countries all over the world, which have to be processed. And I know that a lot of energy is used for this material. So today, the CO2 footprint of a battery cell is only coming 20% from the production in the gigafactory itself. So 80% about that is coming from the production of the material, and a lot is in mining and also further processing of these materials. So that means we need really sustainable produced active and passive materials, maybe also looking for new possibilities. Then we have to have a sufficient or energy efficient and resource efficient production. And I will show you later 2 examples how we can achieve that. Then we need good cell design, closed material circles, and good recycling processes. And these recycling processes, again, should also be efficient. So we should look at the battery cell today already in a way that we can have an efficient recycling. But what can particle technology do in this direction? So from my point of view, so there's a synthesis of cathode active materials. So we need reactors, we need filtration, we need, sorry, I don't know how to get it away. We need de-agglomeration or dispersing step. So we need some graphite spherionization. For example, on the anode side, also a very important process, particle coating, functionalization in a fluidized bed, like Stefan has shown before, or maybe also in a mixer. We had then for producing the electrodes, the dry and wet mixing processes of the battery powders. And today I will show you later the trend is going to full dry processes. So there's a lot of particle technology and machinery required. Then the drying and the compression of the electrode layers, mechanical recycling, also particle and powder characterization. So in the lab, but also online and inline, like Stefan showed, that is also something what is very important. And bulk solids handling and dosing are other things. And another example for in the gigafactories, we will also have a lot of scrap. So at the beginning, we talk about maybe 20% of the material which will be scrap. Later on, probably maybe less than 10%, but still, if it's 10%, we are talking about more than 100,000 tons of scrap a year only in Germany. And this has to be handled somehow. So we have to develop processes where we maybe cut these electrodes, we screen and de-agglomerate our active material, we have to redisperse it and so on. And also we can maybe, instead of a dry process, use a wet process if we then have a wet coating afterwards. So there's a lot to be done. And also we have to develop machinery which is able to do that. And the last point is we need sustainable processes. So we have to maximize the energy efficiency, for example, in all the grinding processes, because about 4 to 5% of the overall grinding or electrical energy goes into grinding. We have to minimize material losses, avoid unfriendly excipients like solvents, which are not water, for example, minimize wear, and also use digital methods. And here's an example, an alternative method to produce battery electrodes, which uses maybe 20% of the energy as today. So we have here an extrusion of granules, and so it's really some particles. Normally it's with a knife, then we cut it like in a pharmaceutical industry. So you get very wet granules, which are here in this small bin, and then you put them on the coating. In this case, it's a calendering coating, so not a typical coating. And as you see with these granules, we can produce really nice electrodes like for a normal wet coating, and this is what we are looking for, and we need much less energy, have a really short duration time, we need much less space for the machinery and so on. But this has to be done and developed regarding particle technology. And what in the moment is really a hot topic also due to Tesla is a full dry coating of these electrodes, and for this we need dry mixing processes with a good dosing. Then we had dosing systems, for example, with this calendering, dry electrode processing, but there are also other methods to produce a dry electrode. You see they have not easy flow properties, I would say, and there's a lot to do to bring this into industrial scale. And with this, I want to conclude. I hope I could show you that there's a high potential or the high need for social and economic, let's say, work to increase the sustainability, of our products today, and also in the field of particle technology. And one major trend is the circular production of products. And one example could be the new lithium-ion batteries. And overall, for all the processes, we have to look on minimization of specific energy, and also maybe using dry processes instead of wet processes to come to a more sustainable future of our world. And now I would like to hand over to Carsten after thank all my supporters and PhD students and so on. And Carsten, he will now talk about the future and digitalization. We heard already some points about that from Stefan, because it's really something what changed in the last 3-4 years. And Carsten, this is his future, let's say, as a young professor. And now he will talk about that here. Yeah.
That introduction. Yes, I will summarize a little bit what's happening in the field of digital twins and cyber physical production particles related to particle technology. Overall, I just can give a small overview on this topic, since the progress in this field of research is enormous at the moment. I will try to find the pointer. And to start with, every digital twin or every cyber physical production system starts with the physical world, which is here depicted in the middle, with certain processes or a process chain of laboratory process or process in the technical scale or even in the production scale. And we have certain process parameters, we have formulation parameters, and at the end, we have online measurements as well as offline measurements. And due to the efforts in the data-driven methods and the digital twin developments, the online measurements and the development of new online measurements is increasing more and more. From these online measurements, we get our data, we have to post-process our data, and then we feed it into our cyber world. That means here we have our digital twins, and digital twin could be a numerical model, as we already have seen for the discrete element modeling, could be an analytical modeling, but could be also one of the more or less new data-driven models. And after that, we get an output of our digital twin. And these output can be then used to make some recommendations to use for process control or have visualizations at the end to have a deeper insight into the process. And these deeper insights into the process leads us several applications fields for optimization. For example, we can optimize the geometry of a single process unit. We can have a process design regarding formulation and process parameters. We can have a process control of our machinery and even of our whole production plant. We have a quality management. We can take a look on maintenance if something happened wrong, or we can take a look on some anomalies in the process. We can take a look on energy and resource management. That means on the sustainability of our process chain or our single process unit. We have production planning and control, or even factory planning and design at the end. And this all is just possible due to the huge increase in the computational power in the last year, which is normally according to the Moore's law. But we have, apart from the Moore's law, which leads to a very slow increase, also the increase in the algorithmic efficiency. That means new algorithms, new methods which are popping up, and also the effort which will be spent in parallelization of modeling leads to a very enormous increase in our computational power, which then can be used to have numerical methods as well as data-driven methods as digital twin to do something for our process in reality. And this is coming more and more since the last years. And if we now starting with the discrete element method or the classical numerical modeling, state of the art is that we are able to simulate nearly all particulate processes along the whole process chain, starting from the particle synthesis and surface modification, the formulation of particles and the further processing, as well as the resulting particulate structures and their properties. That could be, for example, a spray drying process or a dispersion process in a dissolver. That could be like this. This is a CFD-DM simulation of a steered media mill. or we can have 3-phase simulations with an air phase, a fluid phase, and the solid phase in a laminar way, as this drying simulation, for example, or in the middle we have here a 3-phase simulation with a very turbulent fluid surface containing also particles in this shaking flask. And at the end, we can deal with very complex product structures, but we can also use very complex particulate morphologies. And here, just to give an example, here is some coatings from the electrode processing or from the spray drying, or even you can simulate very fractal filamentous microorganisms and their properties. The properties could be electrical conductivity, thermal conductivity, it could be mechanical properties, structural properties, all these things we can nowadays simulate with the increasing computational power. And this is one part of having a digital twin, which gives us deeper insight on the different modeling scales, from a scale of just looking between 2 grinding beads and the product particles, or the whole process in the mill. And additionally, now we are coming to the data-driven methods, which is a new method and a new toolbox of methods containing the well-known artificial neural networks, as well as convolutional networks, hidden Markov models, various genetic algorithms or symbolic programming tools, which can be used based on data. That means they are very suitable for experimental results if we have a lot of data, or especially for the numerical simulations, because here we got a bunch of data and now we can get a better process understanding of these simulations. The easiest way to use a data-driven model is to just use an artificial neural network for a grinding process within such a steered media mill, and then feed in all process and formulation parameters and take a look on, for example, the median particle size. And on the right side, you see the prediction versus the measurement, which matches quite well. And if you take a look a little bit further, you can go to you can even go to particle size distributions with the same number of measurements. Here we are talking about 10 experiments and 10 particle size measurements per experiment. And at the end, you get a measured particle size distribution and a simulated particle distribution. And again, it matches well, which shows the power of this data-driven methods. However, in the most cases, these methods are very limited to the formulation, to the geometry, to the scale of our system. And since they have a black box character. But there are also some methods, some new methods to translate these black box methods into white box models or hybrid models. And just as an example to show how it works for the simulation, here the CFD-DEM simulation of a steered media mill is shown. And with this simulation, you can differentiate the whole mill into voxels. Here you can put in 30 to 40,000 voxels within these mill and then predict the 3-dimensional velocity distribution or stress energy distribution within or with the help of an artificial neural network. That this works is shown here on the next slide, where the mill is cut into different slides, and for each slide the relative velocity in these holes is predicted and compared to the simulation, and this works also very well, and this is based on 10 to 20 simulations. What does it mean? It means if we want to have a full process window and the description of a broad process window and optimize the process, then we can use this artificial neural network to predict values within seconds, where we need 1 to 10 years if we use the simulations, the help of CFD-DEM instead. And this gives us the possibility for very fast process optimization and design, and makes the numerical simulations even much more efficient as it was in the past. There are also the possibility now to not only simulate spherical particles, we can also simulate non-spherical particles of irregular shaped morphologies. And here we can also use the data-driven models to measure 2D pictures via dynamic image analysis or via microscopy, scanning electron microscopy. And then based on these 2D images, we can use existing frameworks to transfer it into average three-dimensional particles, which can be then used again in the classical numerical simulations. And which is shown here, where we have some original particles and then the predicted one based on average numbers, which also works well. All these methods gives us insight into the modeling and how things work. And if we're now thinking about deriving models, for example, for process modeling, then we need fast models, fast shortcut models. And now we have to derive models out of these numerical simulations and data-driven models. And in industry, you have high complex systems, we have high interdependencies, we have budget and time constraints. And the modeling tools have some lags regarding time-consuming, high theoretical results or black box characters. But there are possibilities to combine different methods coming from shortcut models and models from literature, from forces, which are inputs for DEM simulations, and new methods of neural networks, genetic algorithm to create new frameworks which automatically derive these equations and these hybrid models, we call them physical inspired hybrid models, in order to use them in a further for further scale up, for process design, for process optimization, but also for the simulation of a whole process chain. And this is then called cyber physical production system, here we have one method of these. It's, for example, the flow sheet simulation. We saw it from at Stefan Heinrich's slides before, where we have different process units with models behind, which should be hybrid models or at least mechanistic models, and they are connected to other process units with other models. And here we can now handle bulk solids with complex multidimensional sets of distributed parameters. We have unsteady processes. We had shutdown and startup processes, batch and continuous processes. And this is just an example to show how it works, where typically we have a large fluctuation in the product quality and also intermediate qualities, for example, here the granulator output. And with the usage of this flowsheet simulation tools, we are able to get more stable values, and that means a stable product quality at the end of our system. So therewith, I'm at the end of the talk, and I think now we are all open for questions.
Yeah, thank you, Carsten, and thank you, Stefan. As just said, now we are here for answering questions. I haven't seen something in the tool, but Mrs. Dosch, you are the head of the discussion, let's say. Yeah?
Yes, thank you for the interesting talks and presentations. Now at the end, we will bring all the speakers on stage again with me so that we can start our little Q&A session to the talks. The first question which I do have is, how much will the producers of mechanics and equipment for powder processing profit from the new products of energy transition? Could you answer that, please?
Yeah, maybe I start because it was in my presentation. I think a lot. So I hope I could show it that, you know, the new products we now get, and I know that a lot of companies start to plan their factories. They need a lot of equipment from particle technology. So a lot of equipment which is normally seen in the PARTEC will be used in these new factories. And so from my point of view, it's very important. And also maybe we should also include other companies, like companies who are specialized in coatings, more into our particle technology community, because I think to have also view of the entire process chain. And circular economy is also something what is related to that, and recycling, and also separation of particles and all that stuff gets more and more important. So from my point of view, our industry should increase and not decrease in the future. That's my opinion to that. But maybe Stefan, you have what is your meaning to that?
Of course, I have similar opinion, and just going back to also to this simulation possibilities. Yeah, nowadays we can really reduce certain streams, and meaning not only the mass streams, also the energy streams by parameter optimization. So the recursive product design is very important. We want to have a certain outcome of a product, and the computer can calculate what should be the best process chain to reach this, and how should be certain recycles be adjusted. And that is the beautiness. It's not a straightforward simulation, and just to give the boundary conditions and to see what's going on. It's really the optimization of the process by means of computer algorithms, more or less, which came into the particle technology. And that is very, very important, and that is a new tool which is now available. Of course, you need to be an expert in what you are doing, but it simplifies the life.
Thank you both for the answer. We just have received another question from the audience. How do you account for the accumulation of debris in the electrode mass from wear when recycling and processing battery cell materials?
I guess it's again for me. I think that's a good point. I mean, if we recycle products, and especially also, for example, direct recycling within a gigafactory, we have to look for the wear and the contaminations of the product. So one point is to minimize this, to try to avoid that by using good materials, ceramics maybe, which are inert to the battery, so that the battery function is not decreased or not affected. But on the other side, if you look for an end-of-life recycling of battery cells, today I think we have to separate the different materials really into, let's say, cobalt, manganese, and so on, and then bring and synthesize them new. And by these pyro and hydrometallurgical processes, we really can get high purities and get very good materials again.
Thank you for the answer. The next question would be, how do you estimate the reduction of specific energy consumption being possible by process optimization and energy efficient machines?
Maybe I can start, but I think we have to look at what is the ideal case. For example, in comminution, we can't use thermodynamic principles, because then we are very, very bad, because then only the energy of the surface would measure. But so we have to see what is the ideal case. If we in the lab, maybe we grind a particle, and then we have to compare the machines with these lab values. And we know today that, especially in fine milling, or let's say medium to fine milling, we are maybe in the range of efficiency of maybe 20%. So there's a lot of potential, and I know developments in the industry. I can't tell you more about that, but they really decrease the energy by half or something like that. So there's a lot of potential still, but we have to compare it to ideal cases so that we know what is the potential. But Stefan, he is also remoted, or?
No, but was a perfect answer, I would say.
Thank you. Another question just arose. I would just tell the question. is it nowadays also possible to model and simulate the particle generation from a steam stripping coagulation process? For example, coagulate polymer particles from a polymer solvent solution via stream triggered evaporation of the solvent. You can also see the question in the FNA. It was, yeah, a larger one.
Well, that's Stefan, that's not something for you.
Yeah, perhaps it is quite useful to work with the population balance approaches. Yeah, what we have in mind is, of course, population balances that take into account coagulation, agglomeration events, growth terms, nucleation terms, and aggregation is on coagulation is particle combination, enlargement process, and of course it strongly depends on the underlying kinetics. And question is, of course, we have to look to underlying kinetics. We have solved this kind of problems for many different applications, ranging from sintering up to agglomeration in fluidized beds, or calcination in a rotary kiln, etc., etc. It's not so easy to discuss this for this special problem. Of course, it is an interaction between a fluid and a solid particle. We have to look into that. Perhaps we can get in contact. I believe we can discuss this issue in a bilateral manner. I don't know, but it's of course population balance modeling. We have flow sheet simulation tools available for that, and also the complex process is perhaps also important. For instance, precipitation, etc., crystallization. We also have worked on that topic, and that is sometimes one part of a certain process chain, yeah? and with different time constants also. Yeah.
I think the next question is for me, how to derive standard formulated physics or algebraic models from physics-inspired models. The question is, nowadays the tools are available, the data-driven tools, for example, genetic programming, where you can derive empirical models out of the data which describe the process. But the question is how to get a standard model which involves physics, which describes the process very well. And there are also some tools which do this based on physical principles, like the forces behind. You can feed in the physical principles into the code, but the code itself is also searching for example, dimensionless numbers. And at the end, you will get a kind of a hybrid model. But the state of the art is that you have to decide by your own which part of the model you derive is empirical or semi-empirical, and which has a standard format which should be usable also for other geometries, other scales. This is still a human decision at the end. It's also a good point.
Yeah, and of course we also Carsten and Arno are working on surrogate models. Yeah, this is in German Ersatzmodelle. So we can develop surrogate models, but based on physics-based approaches, yeah, and on physics-based properties. And this makes sense if we have a more macroscopic approach. Then we can, as you said, to have empirical, semi-empirical relations, but based on physics. Absolutely.
I think we should develop mechanistic models at the core, let's say, of the simulation, and then the uncertainties and maybe mistakes due to variations, then we have to take care by these data-driven models or the artificial intelligence principles. Yeah. But I think there's another question, and time is running. Yeah.
Right. The next question is, what is the update in Germany on the subject, fluidized bed reactor calcination powered by electric renewable energy?
Yeah, calcination. Yeah, okay. Calcination was of course a hot topic during many years for Autotech, for instance, in fluidized beds and in Venturi fluidized beds. Yeah, it's a bit the question. also work a bit on calcination, have done this to work on calcination, but also in rotary kilns, but also in fluidized beds, but powered by electric renewable energy. Yeah, that is at the moment ongoing, I would say. Yeah, the electric renewable energy is a one part, and the other part is, of course, to understand the calcination. So we have had also some PhDs on our institute on fluidized bed calcination. Could give a more detailed explanation of that if necessary.
But I think it's on the one side decrease the energy demand overall, but on the other side use renewable energy. And I think in Germany we are at least on a good way by having more than 50% from renewable energies, but there's still a lot to do. Yeah.
Now I would like to start with the last question. So at the audience, if you do have more questions, just write an email to partec@nürnbergmesse.de. We will kindly forward the questions so that you can get in contact with our speakers. The last question is, what will be the role of digital twins in particle technology in upcoming years?
Yeah, so I think that's a very good question, since the progress in this field of especially data-driven modeling combined with classical numerical simulation is enormous. And of course, we will see morphing surfaces during simulations. For example, we will see models which replace the classical discrete element simulation, which is also or even done for CFD simulations. We will have new methods instead of artificial neural networks, which are based more or less on combinatoric systems similar to this new transformer networks, which grow and can be extended and evolve during time. I think there are numerous future or potentials we will see in particle technology, which are just limited by our ideas.
And I also see that these methods are not only used in academic institutions, more and more also industry companies start really to have a really closer look on that and hire people to use that. So I think because now it's also starting really in the industry to use these methods, digital twin development and so on, I will see that that's getting a really important factor for the industry. And maybe in 5 to 10 years, if a company isn't able to have a digital twin of his process, then maybe they are not able to sell the equipment anymore, you know, or they have at least a disadvantage against other equipment suppliers.
The basis for everything is data management and measurements, online measurements, to see what is the process doing and how to store the data. This is the basis for all the digital twins which are upcoming in the next year.
Thank you. So we are now at the end, and I would like to say, dear participants, thank you for joining us at the virtual talk today. And I would also like to give a special thanks to our speakers today. Thank you for giving us such an interesting insights of the branch. For you to know, upcoming dates and topics of the virtual talk series can be found on partec.de or on our social media platform on LinkedIn. So stay tuned and feel free to join us again at the next time. And we are also very much looking forward to welcoming you at PARTEC, of course, this year, and PARTEC from September the 23rd until 26th. I'm sorry, it is the 26th until 28th. I'm sorry about that. Have a nice day until then, and see you soon. And thank you so much, Professor Kwade, Professor Schilde, and Professor Heinrich for joining us today.
And please submit the abstracts to PARTEC. Today.
Right, today's the deadline. So if you would like to submit anything, do it today.
Exactly. There will be no extension. Yeah.
Thank you.
Thank you for giving us a possibility here to present our research. Yeah.
You're welcome. It was great having you here.
platform.
Yeah. Bye-bye.
Thank you. Goodbye.
Bye.
Bye-bye.